Hey kids, Smath here. I've got another video in electrons here, and today we want to talk a little bit about noble gas configurations and then do orbital diagrams. Now these are kind of two of the topics that tend towards the end of electron configurations. And so when I'm talking about, oh, that's red. We're talking about a noble gas configuration. That noble gas config is also known, that sometimes it's also called a shorthand, or also called an abbreviated. E-config. So these are ways of writing E-configurations that are going to make it a little bit easier for really long electron configurations. Now, if we're doing something pretty simple like sodium, the idea here, sorry, I'll get to the sodium example in a minute. The idea being is that we can abbreviate an electron config with a previous row noble gas. Okay, no problem. Remember, noble gases, these are going to be column 18. These are the noble gases: helium, neon, argon, krypton, xenon. These are our noble gases, column 18. We're going to abbreviate our electron with that plus everything after. And you'll see the trend here as we do a couple of examples. So in the first one, if we want to do, we've done sodium in the last video a lot. Sodium had an electron configuration of 1s2, 2s2, 2p6, 3s1. Well, the previous noble gas is always going to end in a p6. So we can represent everything inside of the box with the noble gas that has 10 electrons. So we're going to say that would be equal to neon, and then write everything after the box, 3s1. That is a noble gas configuration, or a shorthand config. So you just write the noble gas to take care of everything before that last outermost layer. And this isn't such a big deal until you start getting to something that's relatively large. We start getting to some things that are kind of big, something like silver. So if we were to grab silver, we go Ag has 47 electrons. Okay, well, silver is going to go 5s2, 4d9. Now, silver's kind of unique. It's going to be an exception to filling anyway, but when I say go to the previous noble gas, find the last p6, and then add those up. That's not really what I want. If we add up everything inside of that box, it ends in 4p6. That's going to be equal to 36 electrons. That's going to be an electron configuration of krypton. Then add 5s2 and 4d9. There's the noble gas configuration. And what this does, this conveniently leaves us with the stuff after krypton, and that's the importance. Those are the important electrons that we want to deal with, the ones that do a lot with bonding. We like those. Those are going to end up being some of our valence electrons, is a term we're going to use. And so this is really convenient when we have to draw things that have a lot of electrons in them. Like last time we did iodine. I think we did neodymium. We could do one. Let's grab one of our Fs, something that has a lot of weight to it. And let's grab, I don't know, let's do uranium, just for grins and giggles. Uranium has a lot of electrons, 92 electrons. And so this is going to take us a little while, but patience. 1s2, 2s2, 2p6, 3s2, 3p6. All I'm doing is following the filling order that we learned when we did diagonal fill diagrams this week. 4p6, 5s2, 4d10, 5p6. Rearrange in the next line, 6s2, excuse me, 4f14, 5d10, 6p6, 7s2, 5f1, 2, 3, 4. That's a full electron configuration. That's 92 electrons right there. Now, go back to the previous P6, right there. Everything up to that point can be represented with radon and 7s2, 5f4. That is a whole lot easier to do than the full electron configuration. Now, when we come back to school, we're going to talk a little bit more. Next week, we're going to talk about how we can get that without having to write out the big, long string. Remember, I've told you, we can get all these electron configurations from our periodic table. So if we have a periodic, we can get an electron configuration and vice versa. So that's how we do these noble gas or shorthand configurations. That's one topic. Now, the other thing we wanted to talk about in this video was going to be called an orbital diagram. And an orbital diagram is just a visual representation of an E-config. Of course, you already know our first example has got to be sodium. So if we do sodium, what we're going to do, we've got 11 electrons. So we're going to draw orbitals now as dashes. And the y-axis here is going to be increasing energy. So the first and lowest energy electron that we're going to have, or orbital that we're going to have, is the 1s. And then the next energy we're going to have is going to be the 2s. And after the 2s, we fill the 2p. We're going to keep our s's. Then over here, we're going to put our p's. Here's our 2p sublevel. Then we're going to come back. Next one we need is our 3s. And now I can put electrons, and I'm going to represent electrons with an arrow, a half an arrow actually, because electrons have a half a value. And those electrons can be arrow up or arrow down. So that would be the same as saying 1s2. Then I could do 2s2, 2p6, and we have one more, 3s1. Now, if I count these, I should have 2, 4, 6, 8, 10, 11. That's my orbital diagram for sodium. It really is just the electron configuration laid out with all my S's in a row, all my P's are going to be in a row. When we get to one, we're going to have our D's out here. We're probably not going to do an orbital diagram with an F orbital. That's going to take us a lot of electrons and a big piece of paper. But let's do one with a little more electrons, a little more meat to it. Let's do, I don't know, bromine. Bromine is 35. So we're going to grab Br, 35 electrons. And so I'm going to stack up, try and give myself room. 1s, 2s, 2p, 3s, 3p, 4s. Then remember, after 4s, we're going to fill, then after 4s, we're going to fill 3D, 2, 3, 4, 5. There are my 3Ds. And then after 3D, we're going to fill the 4 Ps. 1, 2, 3. There are the 4 Ps. So now you see I'm setting them up so that my S's all line up, my P's all line up, my D's all line up. And I've got 1 orbital, 3 orbitals, and 5 orbitals in each of my sublevels. And now I've got 35. And now it's just a matter of going from low, jump to the next level, jump, fill up this level, then jump to the next highest. This feels like an old-fashioned arcade game called Frogger, where we just keep filling and jumping. 1, 2, 3, 4, 5, 6. We need to fill those orbitals in that order, okay? Then we go 1 and 2. So now I've filled about 20. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 of these, okay? And what I mean in that order is when I come to a sublevel that has multiple orbitals, every orbital gets 1 electron before an orbital can receive a second electron. That's called Hund's rule. Everybody gets firsts before anybody gets seconds. Now we had 20. I just added another 10. There's 30 electrons. I've got 5 more electrons to fill. Up, 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 down, down. That's an orbital diagram for bromine. Okay? All we're doing is showing a visual representation now for me to see bromine has 1 unpaired electron. And guess what? When we get to bonding, we're going to find out that bromine forms 1 bond. That's the way that this works. Okay? So try to remember Hund's rule. That's important enough to be in red. Hund's rule basically states when filling energy, filling orbitals of equal energy, every orbital gets 1 electron before a second electron. And of course, the other principle that we still have to follow through at this is the one we've been using the whole time, which is called the off-bow principle. And that states that we're basically going to, we fill orbitals from low energy to high energy. So as long as we're following the off-bow principle and Hund's rule, we can get orbital diagrams that are nice, neat, organized, and will tell us how many unpaired an electron or an atom has And that's going to be how many bonds it's going to be capable of making. So you can see with this, these aren't just decorative ways of writing them. They're functional ways of speeding things up with abbreviations and showing things visually with electron orbital diagrams. I'm Smath. I sure hope that this video helps you. I look forward to seeing you in the next one.